two things in our schedule is first we'll have a short talk from Adam Goldstein, a little bit out of the rest of the flow of the short talks because he is on a very different time zone and he's already at like 11 p.m. I think in Japan right now, right?
Yeah,
So
11:30.
yeah, so appreciate you for joining at this late hour. Um, and and then, yeah, so that'll be for about 10-minute talk and a couple minute questions. Um, and then we'll go to a mindfulness practice led by Martin for another 10 to 15 minutes to kind of get out of the whole discussion and mind mode into a bit of presence and experiencing mode. Okay, and with that, let's get into it. So, Adam, if you want to like introduce yourself real quick in a way that feels informative of
Yeah,
this, yeah.
yeah. Hi, everyone. Thanks for having me for this short talk. I'm calling in from the Artificial Life Conference in Kyoto, and my background's in computer science and biology. I studied with Mike Levin a few years ago, and now I'm the co-founder and head of research for Softmax, which is an AI company that looks at how AIs and humans can form collaborative, emergent collectives. So I'm going to give a short talk today on the math of what we call organic alignment, which is in our definition is the sort of the way that you can form a larger whole that cares for the parts, so they all benefit. And just to give an overview, we are thinking about alignment very differently than other AI companies that are very focused on control, very focused on top-down control. We're instead looking at how can AIs solve problems in groups and measuring whether those collections are forming a larger whole, sort of like an AI super agent or a super organism. And we want to see whether those super agents are good for the AIs and humans that are part of them. In other words, is it a healthy super organism? And eventually, we want to create and sort of develop and engender collectives of humans and AIs in which they both benefit, so that it's truly a transcending and including of both. The model for this is healthy biological systems, so multicellular life, symbiotic relationships. These are the analogies that we like to use. But up until pretty recently, there was not a lot of formal math that could help us with this. That started to change, and that's what I'm going to be giving a short overview of today. So the first thing to understand is that emergence, and I'm sure you guys are talked about this, you're going to be talking about this, emergence doesn't negate the parts. When you have a collection of AIs, operating, all of the AIs are still there, just like all the cells are still there in an organism, all the molecules are still there in a cell. The question is there this level of emergence that's taking place? That's the first question. And we need formal math to answer that. But even if there is emergence, that's not sufficient, right? Because you can have emergent relationships where parts form a larger whole with meaningful, wholeness, but it actually hinders or hurts the parts that are part of it. You can have a parasitic relationship or a repressive dictatorship, right? These are cases where there is a higher level of organization that develops, but it's not actually good for the parts. So the way that I very kind of cartoonishly describe this is that there's a sweet spot at the intersection of positive emergence and the benefit to the parts. And that's what we want to be able to measure. So I'm going to give it a quick overview of a paper that we sponsored that came out earlier this year on the question of measuring emergence. This may be relevant to folks in this group who are interested in this question. And it's called Causal Emergence 2.0. The idea is that you want to be able to quantify the extent to which a system is governed by the whole as opposed to by the parts. In other words, how well can you predict the future if you look at the whole as a whole versus if you look at each of the individual parts on their own? And there's a formalism for this based on Markov chains, which some of you may or may not know. I'll just give a short overview. The idea is that you can take a system and divide it up into states that transition between each other from one state to another. And if you look at this, you can basically color the graph so that step by step, you're coloring all of the connected parts the same color. So you can see that, 4 and 6 and 7 are colored the same. And as you progressively color these the same, you discover that at a certain point, you've actually carved it up at the joints. You've colored all of the connected states one color, and then you've also colored each of the disconnected states a different color. And at this point, you can predict the future color of the system perfectly. If you're in a blue state, you're going to end up in another blue state. If you're in an orange state, you're going to end up in another orange state. If you're in a yellow state, you're going to end up in another yellow state. And by doing this coarse graining, you can effectively, say, oh, these are the states of the system that can effectively be treated as one. And these are the states of the system that can't. And as you keep coarse graining beyond that, you don't increase your predictive power at all. And the takeaway from this is that there is a coarse graining or a set of coarse grainings and systems that are the ones that actually help you to cluster or group together the parts that to a first approximation can be treated as the same. And if you apply this to any complex system where you have access to the states, you can actually derive a metric for what level of the system the causal emergence takes place. In other words, what coarse graining of the system allows you to best predict what's going to happen next. Now, in this example, it's a super clean example because the predictability reaches 100% as you coarse grain. In general, it's not so good, right? In general, systems are more complex than this. So you may not get the ability to perfectly predict the system, but there may be certain coarse grainings that let you predict it better than others. And those are the areas where you would see positive causal emergence according to this approach. So we're starting to use this in our own research with how multiple AIs interact with each other. We think it'll also be relevant to other researchers working on similar questions. The next question is the question about how the parts benefit or not. And here, if you can treat if you want to understand the collective benefit, you can take metrics that you might use for single agents like reward or variational free energy, and you can look at them at collectives at the level of collectives. So you can see whether a group of AIs, through forming an emergent whole, actually also help themselves improve their reward or their loss or their free energy. So that's a sort of very first order way of answering the question. There's also an approach that Carl Friston and some collaborators put out a few years ago, which looks at a mathematical model of valence. So you could ask, not only is an AI, is it achieving its, target loss or something like that, but how confident is it in its own model of the world? In other words, how have its beliefs about its beliefs changed? And the more confident that an agent is in its beliefs, and the more consistently that its confidence is justified, in other words, it's getting what it expects, according to their argument, that's like a form of positive valence. So these are just directional ideas to sort of paint the landscape that you can think quantitatively about both emergence and the question of whether the parts benefit. And that can provide very useful tools if you're working in, AI research or any kind of quantitative agent-based models for understanding what's going on. But this is really just the start. What we're working on now is a notion that we call care attractors. And we mean this in the sense of complex system attractors like self-sustaining patterns of behavior, specifically self-sustaining patterns of care. How can you create a situation where AIs care not just for their own well-being, not even necessarily for their friends' well-being, but care for the well-being of the entire collective? How could you be rigorous and define that and measure it empirically? And this means shifting from just understanding alignment as a thing that happens. Oh, a system is now in this state, to instead thinking of it as something that can be engineered and stabilized. So how do you get the parts to care about others and to care about the whole? How do you make that part of their model of the world and part of their dynamics? And then how do you make sure that that sustains over time so that the agents are actually in a loop where through caring for the whole cares for them, they then have continue to persist and care for the whole and vice versa. And we define care very sort of mathematically as having a preference over coarse-grained states. So I, as a person, might care that the people in my family are happy, right? And I might distill that down to there's no argument happening right now. There's no yelling happening right now, or everyone is smiling right now or something. Those are, obviously approximations, but they get at the idea that you're taking all these different variables and you're coarse graining them into a single metric. And if agents care about a single metric of their collective or a set of single metrics, then in our model, that's a sense in which they care for some property of the whole. They're acting to sustain that property. This connects directly to the math of causal emergence, because if the agents care about some coarse-grained state of the system, then that coarse-grained state of the system has causal power over the agent's actions. If it changes, the agent's actions change. So in that sense, the whole develops its own causal power over the parts, and the parts care for the whole. So that's how we intend to complete the circuit. And from that standpoint, you can then walk the ladder of alignment. At the low level, you can have alignment that's just inborn, right? Cicadas all swarm at the same time because they're born to do it, right? That doesn't require any creativity or any intelligence. You can have physical alignment like schools of fish, where they just follow each other. They don't even need to know that the other fish are living beings. They just need to know that they're a thing that they can follow. And you climb up, you can have emotional alignment, where agents have a model of what other agents are feeling. And you can have goal alignment, where agents have a theory of what other agents are trying to achieve. And you can have group alignment, where agents are trying to model what other agents identify as. And culture alignment, what do other agents identify as? What beliefs do they hold in terms of ideology? And hopefully, I mean, Thomas hopefully will help us with this. They can get to a level where they just know deeply and intrinsically that they are part of the same whole. It's not a conceptual thing. We're not quite sure how to achieve all of these, but this is the roadmap that we think about applying the notion of parts and emergence and benefit and care to building a world where, humans and AIs can get along, and we can know ahead of time that that's going to be the case. And we hope not only that, we can build a better multi-agent world with AIs, but that you can also think of this as, something that applies to cancer, to aging, to political polarization, to economics. You could ideally use the same tools from complex systems to have an impact in all of those areas. So if you're interested in this, if you're a mathematician, you want to chat some more, send me an email. We're looking for researchers to collaborate with to formalize some of these ideas. And otherwise, I'll just open it up for questions.
Beautiful. Thank you. I love the idea of parasitic versus symbiotic relationship between the whole and the part. I've never
Yeah.
thought about that before. So, uh, anyone has questions?
Neil, looks like you have a question.
Yeah. Um, so the way I think about complex systems, um, one way I think about them is in terms of the balance between negative and positive feedback loops between agents comprising the system.
Yeah.
And on your last slide, to me, all of those reflect when positive feedback loops escape from negative feedback loop control and start to
Yes.
power up into energy expansion, rapid expansion, energy expenditure, and then collapse. How is there a way to map that way of describing it to what you're talking about, what you're doing?
Yeah, well, I use the term attractor on purpose because it is this sort of positive feedback loop. You could also imagine, and we talk about this in a paper we're working on, the notion of a care repeller, the opposite of an attractor, where somehow because of the way that the agents are interacting with each other, they're actually causing their group to collapse, right?
Mhm.
That could be like a negative feedback loop or potentially a
Oh,
negative feedback loop. So, yeah.
yeah, I would use them negative feedback loop.